Okay. So, hello everybody. I'm really happy to, whoa, sorry, there was the sun. I'm really happy to be here and talk a little bit about deformation. So everything will be looked from a mechanical perspective, but monitored with geophysical tools. So, and I'm going to discuss different scales and what we can do at all those different scales and why we do that in the lab. So, why do we do stuff in the lab? Well, if we go back on the video, and if we stop here, that's what rock mechanics people do. So we just basically take some rock samples, we put them in our lab, and we try to crush them and monitor as much as we can over there. So, and the thing is that, I guess that the reason why we do that is because we're control freak, and we try to control all of the parameters that we can control. On the other hand of the spectrum, you have all of the people who are making observations. So this is a drawing from a friend of mine. So she's doing some GPS and seismology and everything. And so she's putting stations around the world and trying to have an insight of what is going on around natural fault zones. And I guess that the goal of everybody is try to make sense out of the comparison between both and constantly try to go back and forth between the lab and the field. Because both of the methods have their advantages and we can learn lessons out of both. So as I mentioned, in the lab we have full control of parameters, we can over-instrument everything, but we're just looking at the lab scale. So we have a problem in space scale and in time scale. Whereas the colleagues from the field, they are looking at reality and what we are really interested in. But unfortunately, they can't really put as much sensors as they would like. And there are many, many things that are unknown. So that's the reason why we have problems in some understanding of the physics behind what's going on in the field. And so the approach that I'm working on is to try to upscale step by step and try to go from the micro scale to what I call the in situ scale, which is around 10-meter scale. And I pass by in the middle with the triaxial testing, which is the classical rock mechanic thing. So let's go to the micro scale. So we had some insight from the presentation of Declan earlier. So what we do when we do micromechanics is that we take tiny little samples and we try to image them over time, meanwhile deforming them, and we do digital image correlation. This can be done in 2 dimensions or in 3 dimensions. I'm going to show you some results of some 2-dimension experiments. So we take the initial image and we're looking for the same grid in the deformed image, and then what we recover from that are continuous strain fields that we have of the surface of our sample. So I'm going to show you some different results from SEM images and also from optical measurements with a stress concentrator in the middle in order to see what happens and how you do localize at the microscale the deformation. So what do we do inside of the SEM? So we take a tiny little sample of 16 millimeters length. We flatten the surface and then we polish it with an iron polisher. And then we load it slowly because we are inside of an SEM and it's an environmental SEM, so it takes forever to take pictures. So we load it step by step. So we load, we wait for everything to relax, so nothing is moving. Meanwhile, we're taking the picture, and then we take pictures. And so, if I continue a little bit, so we have wonderful pictures. So this is a clay sample. So you have the bedding that is taken, that is vertical on the picture, and we're loading horizontally the sample. And so to convince you that I've been loading it, I'm just taking the naked picture. This is a stitch of 12 images. So 3 on the vertical and 4 pictures on the horizontal, which is also the reason why it's taking forever to take all of those high resolution pictures. And we load it. So if you look carefully, you see that the picture is moving. So despite the fact that it's really pretty to see stuff being like moving on the screen, we can also quantify everything, which is the reason why we do that. So when you interpret the previous picture that I've been showing you, then you can really see where you're going to localize the deformation. So from the colors, you're going to have in pinkish colors the strongest compaction that the sample is really going. So this allows to see, for instance, in the case of clay-rich, clay-rich shale, whatever you want to call those ones, that you're going to localize the compaction mostly in the bedding. I mean, that seems pretty obvious, but actually, as long as you don't really see it with your eyes, it's really, I mean, there are also other mechanisms going on, but it's also a really nice way to really quantify what type of mechanisms, because there is not always just one type of mechanism occurring so that to localize deformation. So that's the reason why we want to use this kind of tools. But then if you go one scale up, so if you look at optical experiments, what you can do is just de-zoom a little bit, so you know potentially where your failure is going to happen and where everything is going to take place. So what we did is that we took similar sample, anisotropic samples, because anisotropy is fun, and why not? And we made a hole in the center in order to concentrate the stress and to know where we should look at. If you deform an isotropic sample, you're going to have the localization of your fracture at the tip of your stress concentrator. And so here is the setup. You have a camera that is taking pictures. We're taking 4 pictures in a row. This is going really quickly. So we can have the 4 pictures in 12 seconds. So really quickly is kind of a relative thing. But and then we try to track what's going on in our sample. And so the sample I'm showing here. So the bedding is horizontal, and we're loading vertically. And so it's quite quickly, so that we have time. So the pictures are taken quite quickly, so that we have time to see the propagation and what is going on. So what you see is that at the beginning, you have what you expected to happen, so fracture propagating at the tip of your stress concentrator. But actually, the final mechanism for failure is not going to be just a simple mode 1 crack opening here. You're going to have those staircase fractures that are going to happen. So you see one here, and also one really pretty here, that really looks like what is happening on the field. So we wouldn't have been able to see that with classical deformation, which is the reason why those optical experiments are really important. And also we've been highlighting the importance of anisotropy and fracture pattern, because if you repeat that kind of experiment on different samples with different anisotropies, you're going to have different fracture patterns. So this is the one that I've been showing with the staircase fracture. And this is with a vertical bedding. So you see that in that case, you're just opening the bedding, which makes sense, to generate the fracture. And when you have a 45 bedding plane sample, then you're simply slipping towards your bedding plates. But what is really pretty is really that beautiful fracture shape, and I would like you to keep that in mind for the following. Then I will try to go quickly onto actual testing. So this is something that has been done for quite a long time. So what we do, Manuel started to show the setup. So this is a slightly different setup here. So you put a sample in a jacket, and then you can put all of the sensors that you have space to put actually around it, acoustic sensors, strain gauges, and so on. You put everything in a loading cell, you put confining pressure, and then you apply your deviatoric load, and you crush the sample. Meanwhile, doing that, you're going to measure the deformation, so you're going to measure the axial strain, you're going to measure the radial strain, and the evolution of the volumetric strain. And if you're lucky enough to have those acoustic sensors, you can measure everything actively and passively, Actively means that you're going to listen to acoustic emissions, but I'm not going to show you any acoustic emissions today. I'm just going to show you some result of P-wave velocity evolution during deformation. So if you just listen, if you just actively measure the P-wave velocity, you're going to, at the beginning, meanwhile loading, you're going to have an increase of the P-wave velocity because you're compacting everything in your sample. And as soon as you start damaging the sample, you're going to have a decrease of your P-wave velocities. And that should give you an insight of what type of mechanisms are going on in your sample. But what you usually just detect is the damage occurrence. And by damage, in that case, I just mean the crack formation. So if you do that, again, on something anisotropic, then you can, so it's a sample with a horizontal bedding, and we're measuring P-wave velocity evolution at different ray angles. So in red, you have the evolution of the stress strain curve. So basically, we're just trying to crush that intact sample and to see what is going to happen and what are the mechanisms of deformation that are going to take place inside of our sample. So we are at relatively high confining pressure, so 80 MPa. And what is happening is that we have a very long plastic phase. What was really interesting in that specific test is that usually in that type of rock, you have the horizontal velocity, so the velocity in the bedding that is the fastest one. So it's the really light color that are on the top. And then the velocity is decreasing when you go through the bedding planes. In our case, really early in the loading phase, we started to decrease the velocities. And the other velocities were starting to get faster than the horizontal velocities, which means that actually when you strongly deform your sample and when you're at high confining pressure, so at depth, you're having a rotation of your anisotropy in your sample, which can be an explanation for the structure of fault zone and for the variation of stress field around fault zone, for instance. And so it's a strong indication that you don't just have a crack forming, but you also have some rotation of minerals around your fault zone, which is really a very important observation of fault zone. And so that's what you see if you try to reinverse all of the velocities in your sample, but I should not go into details. But you nicely see the fact that you have, so normally you have your bedding that is horizontal here, but you nicely see the reorientation of minerals on the post-mortem microstructures. And currently what I'm doing with some of my colleagues is try to take the best of both worlds, so try to look at digital image correlation and combine that together with active and passive seismic measurements in the lab. So this is our first test on salt samples. So what you see in green is the stress strain curve of our salt sample. We have a different phase in the localization of our deformation that we looked at. So there is a problem of parallelism, but what we see is that we see the localization quite late on the surface of the sample, but we see prior to that a drop in the velocities that are represented in blue. So we try to combine those two in order to be able to quantify the loss of velocity with the mechanisms that we observe with the digital image correlation. Yep. And let's go to what I'm calling the in situ scale, and many people are calling it that way, actually. We can do different type of things at that scale. So in order to do that, you can go to what we call underground research laboratory. So those laboratories are dedicated to research, and you can basically do whatever you like there. So I went quite a number of times in Tournemire, which is located in southern France, and which is the experimental tunnel that belongs to the Nuclear Safety Institute in France. So over there, you're crossing a layer of clay, which is the reason why I'm working a lot on clay. So you have that quite thick layer of clay, and it's crossed by a tunnel. So that tunnel is in white, is that tunnel that you can see in gray here. It's the main gallery, and then you have those experimental galleries that have been drilled afterwards. And we're lucky enough there because we have a fault. So there is a fault zone, which is a minor fault zone, of course, a baby fault here that is fully localized in clay-rich material. And so by clay-rich, I mean more than 50% of clay material, which is the reason why it's strongly anisotropic. So the first thing that you can do is, so there was an experiment taking place here, but I'm just going to show you the petrophysical measurement that we've done on one borehole that is crossing the fault zone. So usually when you describe a fault zone, you put everything into categories because we're scientists, we like to categorize stuff. And so when you drill through the fault, you look at the samples that you're recovering, and then you distinguish the intact zone. It's really boring, it's clay, it's gray, there is nothing going on over there. Then you start getting inside of the damage zone that can take really different shapes. So you can have those, you can have small fractures, fractures filled with calcite and everything, but in between everything seems to be really intact. And then, of course, at some point, because you know where the fault is, and you've been drilling toward the fault, so you're going to cross the fault core at some point. And in our case, we were lucky enough to recover part of it. So the fault core is that kind of muddy thing with scaly clays. You have a difference in colors. Everything is extremely disturbed. So we made our description just by looking at the cores. And then we've done some measurements. Sorry. So the first measurements that we've been doing are measuring the porosity that is denoted in blue and measuring the dry density of the sample. So I put on the back of the figure the zoning that we've been putting just by looking at the cores, and then I just put the measurements that we've done. So it looks like things are not as easy as we thought it was. So actually, it's not like a strong transition between one zone to the other. Everything is really smooth. We have something quite constant in terms of properties in the intact zone, and then we start to have more porosity toward the damaged zone. Everything is becoming a bit crazy in the fault core, and then back to normal. It's a little bit asymmetric. There is a shorter damage zone on one side than on the other, but we can go back on that. And also what we've done is that we measured the evolution of the anisotropy of P-wave velocities between the intact zone and the fault core. So what we do actually is just bringing the field inside of the lab. We use our lab classical measurement to try to quantify what's happening on the field, and we have a strong velocity drop when we get in the fault core, and we have a loss of anisotropy, which is really similar to what we observed when we were deforming by ourselves our samples. So that was just an example of what we could do, and if you combine experimental data and petrophysical data and so on, you can come up with some kind of idea that fault zones are not just one single discontinuity that we should look at. So it's a whole system that should be integrated, and so it's everything is really smooth, and we should potentially look much more at the damage zone and at the surroundings of the fault. And finally, I'm going to talk about the project chenille, which means caterpillar in French, which is the reason why there is a little caterpillar. So the idea of the chenille experiment is to go back to Tournemire. So we went back to Tournemire and we installed everything there, and to perform coupled thermohydromechanical loading on the fault zone over there. So we've been drilling 9 boreholes. So 4 boreholes are for heating, so 4 boreholes are for heating, and then we have some monitoring boreholes. So we are going to impose a heat load on the fault and to stimulate it together with an injection probe containing air. And we are going to monitor everything with fiber optics for temperature and passive and active seismic monitoring. So this is a cross section. So in the middle you have the injection borehole. The 4 red dots are the heating probe that we installed, and this is the expected heat that we're going to generate. Plans are changing a little bit because we have problems with the heating probes, but initially we were targeting to reach a temperature of more than 100 degrees in order to impose some changes in the mineralogy of clay. And heating a rock mass is taking forever. Basically, if you want to reach 150 degrees, you need to have to wait for more than 200 days. And everything is really expensive, so we can't always do that. So we've been installing, so in the red boreholes, so parallel to the fault, we've been installing heating probes, DTS fiber optic to have a continuous measurement of the temperature. And in the fault, so on the blue part here, we've been installing an injection probe. So we have 2 packers, and we inject pressurized air, and the upper part of the borehole is fully cemented, and we have also DTS to measure the temperature in the injection borehole. And we've been also doing different campaigns. So I will just show you the preliminary result of the first active seismic campaign. So we've been putting those boreholes for active measurements of seismics with a hammer source. So the source is here. So it's an automatic source, and we've been recording the difference of P-wave velocities. In between, we've been adding a new borehole here, so we get a better resolution because the fault should be here. But what you can see is that we start imaging the fault, which is actually quite a challenge because usually fault in clay-rich material are really hard to resolve, especially when you have a small shift in the fault. And we are also going to listen to everything with passive seismic. So those are acoustic sensors, but made for the field. So we hope that we're going to generate something that we will be able to listen to. And just to finish with everything, so I started to show you the 3 scales. I will just add another one, because now that I moved, there is a beautiful machine where I am installed now. The machine is called Dimitri, with a very French name, Dispositif de modélisation analogique triaxiale. So this machine is a giant baby that can take samples that are 1.5 by 1.5 by 1.5 meters. You have a crane to carry your sample and so on. And so the idea is to do solid mechanics in an analog way on weak material in order to try to see what we can generate. And so the machine is not, the machine exists, but it's not equipped yet. So if any seismologist is wishing to come and play, you would be more than welcome. So thanks for your attention.